Good evening, everyone. My name is Cooper Nicholson, and today I'll be presenting Lab 3 for Physics 2212, which is focused on circuits. The purpose of this lab was to demonstrate how current and voltage behave in different circuit setups containing resistors and capacitors. Using multimeters, we measured both current and potential difference to compare real data to theoretical predictions. In summary, we found that the current stayed consistent throughout the circuit, the sum of the potential differences around the loop was approximately zero, and the charging and discharging times of the capacitors were nearly identical. Before getting into the results, let's briefly review the physics behind the experiment. The node rule states that current entering a junction equals the current leaving it. The loop rule says that the total voltage changes around a closed circuit must add up to a zero. Ohm's law connects voltage and current and resistance using the equation V is equal to IR. And finally, capacitance is described by Q is equal to CV, showing that the charge is proportional to the applied voltage. These principles help predict what should happen in each of our circuit tests. Our first setup was a series circuit built from batteries, wires, ammeters, and resistors, which was our system. The surroundings was all other things. The predicted current, calculated using Ohm's law, was about 2.04 milliamps using a 3-volt supply and combined resistance of 147 ohms. Additionally, we found 0.93 volts across the 47 ohm resistor and 1.95 volts across the 100 ohm resistor, confirming current consistency across components. All measured currents were around 19 milliamps, validating that in series circuits, current remains constant while voltage divides proportionally to resistance. Next, we analyzed the potential difference graph and answered conceptual questions. One question asked why the current didn't change when adding a voltmeter. The reason is that the voltmeter is designed with very high resistance, so it draws almost no current and doesn't affect the rest of the circuit. We also looked at how the system would behave if it were in parallel instead of series. In that case, the current would increase to about 50 milliamps due to the 1/r relationship, since total resistance decreases when components are parallel. Lastly, we compared measured resistances to theoretical values and found small variations, about 48.7 ohms for the 47 ohm resistor and 102.6 ohms for the 100 ohm resistor, which shows our instruments are accurate but still subject to slight experimental error. After F on this graph as well, the ohms reached zero. In the next part, we studied an RC circuit with a resistor, capacitor, and light bulb. During charging, the bulb started bright and dimmed as the current diverted into the capacitor. During discharging, the bulb began to dim but brightened as the current left the capacitor and re-entered the loop. Our measured charge and discharge times were both around 2.7 seconds for 10 ohm resistors and 11 seconds for 20 ohm resistors, showing symmetrical timing and confirming that the process is consistent in both directions. Finally, we reviewed sources of error, and some sources of error could be an equipment error, which could include voltage loss through imperfect wires or small inaccuracies from the ammeters. Human error could also have played a part, as including loose connections or inconsistent clamping, which introduced extra or not enough resistance. For our what-if scenario, if we charge the capacitor without a resistor, the ideal model would predict instant full charge, but in reality, all circuits have some internal resistance, so instantaneously charging is almost impossible. This highlights the difference between ideal theory and real physical systems. To wrap up, this lab reinforced Ohm's laws and capacitor behavior. The current remained constant in series, voltage sums approached zero, and the capacitor's charge-discharge pattern was consistent. Overall, these results strengthen our understanding of how electrical circuits distribute energy and maintain equilibrium. Thank you for listening.